So hello everyone and welcome back to Hope Coaching Institute Private Limited. Here we are with another numerical on thermodynamics. As you all know that we are continuing with thermodynamics numerical series as well as the theory part. So for more of lectures of theory, you can visit the YouTube channel of Hope Coaching Institute, as well as some basic numericals also I have taken there. Now, this is a bit advanced numerical of thermodynamics, not a basic one. So let's see what it is. The question is, consider a classroom of dimensions 5 multiplied by 10 multiplied by 3 meter cube. So these are the L, B and H, length, breadth, height, the dimensions of a classroom at given temperature and pressure of 20 degrees Celsius and 1 atmosphere. There are 50 people in the room. So the classroom contains 50 people. Okay. Each losing energy at the average of 150 watt. So 150 watt means 150 joules per second is the energy lost by each and every person which is present in the room. Assuming that the wall, ceiling and floor furniture are perfectly insulated and none of them is absorbing heat, how much time will be needed for rising the temperature of air in the room to body temperature? So our body temperature is 37 degrees Celsius approximately. So the question is about the time, that how much time will be needed, to see. You can see this, how much time will be needed for rising the temperature of that air that is present in the room. Initially the temperature is 20 degrees Celsius, as you can see, and they are asking for the heat required to raise the temperature of 20 to 37 degrees Celsius. So we just have to calculate the heat that is needed to heat the room, the enthalpy changes, and then we have to see that what is the enthalpy changes that are happening in the room, and then we have to compare both the entities. So for air, the value of Cp is given 7 by 2 of R. Here R is the universal gas constant, and loss of air to outside as the temperature rises may be neglected. So this also has to be taken. There is no loss of air to the surroundings as the temperature is rising. Okay. So the core concept of latent heat has also to be neglected now. So let us start with this. As I told you that we have to calculate the heat needed and heat released. So for that, we firstly have to take the dimensions of the classroom and calculate the volume of air, because air is present at all dimensions in the room. So volume of air in the room initially. So volume of air in the room will be equal to the volume of the classroom, which is L into B into H. Directly we can calculate it. So the dimensions are in meter cube. So this becomes 150. Okay. So this is 150 meter cube, and we can convert it in CGS terms, which for which we have to multiply it with 10 raised to the power 6 for each meter. For each meter, to convert it into centimeter, we have to multiply with 10 raised to the power 2. So for meter cube, we have to multiply it with 10 raised to the power 6 to convert it into centimeter cube. So this will be the volume of the classroom as well as volume of air in the classroom. Now next, with this, we can use the ideal gas equation, which is PV equals nRT, and we can calculate the number of moles. So number of moles will be PV by RT, and we are given with all the situations here. Pressure is 1 atmosphere, which is not changing, multiplied by volume. Volume we have calculated 150 multiplied by 10 raised to the power 6 in centimeter cube. The value of R, also has to be taken. So in centimeter cube, that will be 0.0821 multiplied by 10 raised to the power 3. Okay. And multiplied by the temperature, initial temperature is 20 degrees Celsius. So 20 degrees Celsius means This is 273 plus 20, which gives us 293 Kelvin. Okay, so initial temperature also we should put. So this is 293. So on substituting all these value, I'm writing the answer which will come out. This will come out about 6.236 multiplied by 10 raised to the power 3. You can check it out by solving yourself. So this will be the value for number of moles of the air. Let me write it. This is number of moles of the air. So volume of air we have calculated, number of moles of air we have calculated. Now we can calculate the heat needed. Now how to calculate heat needed? We'll use the formula for delta H, which is the enthalpy change, and it's equal to N. Cp is also given, delta T, change in temperature. So N of air we have taken out the value, which is 6.236 multiplied by 10 raised to the power 3. This is N, and the value of Cp, as you can see here, the value of Cp is 7 by 2 of R. So 7 by 2 multiplied by R. So use standard value of R, which is 8.314, and then we have to take the change in temperature, so delta T. So initially temperature is 20 degrees Celsius, and what is the final temperature? It's 37 degrees Celsius. So it's 273 plus 37. So this becomes 310 Kelvin. So we have to take out the value for delta T, 310 minus 293. So using this we can calculate delta H. You must also remember one thing, that here we have used the value of R as 0.0821 multiplied by 10 raised to the power 3. If we use the value of 150 multiplied by 10 raised to the power 6, since it was in centimeter cube, that is why we have converted and used the value of CGS unit of R. So this is CGS value of R in centimeters, and where pressure is in atmosphere. So this has to be taken in mind, and temperature is in Kelvin. So now we have used the value of R as 8.314 because the answer will be in joules. So the value for delta H will come out in joules. So I'm writing the answer. You can solve this all by yourself, and this comes out to be 3.085 multiplied by 10 raised to the power 6 joules, around this approximately. This will be the value for delta H. So you can pause the video and note it down, and we will continue. Okay, so let me erase all this and use the value for heat needed. So the delta S that we have calculated just now is actually the heat needed to heat the room. So this delta H that we have calculated, this is heat needed to heat the room to 37 degrees Celsius. This was the question. From 20 we have to heat it up to 37 degrees Celsius. So we have calculated the enthalpy changes for that, which was around 3.085 multiplied by 10 raised to the power 6 joules in SI units. Now this is the heat needed. Now what is the heat released? So heat released by 50 people that are present in the room. So each person releases an average energy of 150 watts. So 150 watt is 1 watt is equal to, well, let me write it here, 1 watt is equal to 1 joule per second. So it is 150 watts. So 150 joules of heat is released by each person per second. So there are total of 50. So we have to multiply it by 50. So this will give us the value for total heat that is evolved by 50 people in the classroom, which is 7500, I guess, joules per second. So this will be the value for heat released. Now 7500 of joules is released per second, and this is our aim. This much heat is required or needed. So we will just calculate the time. This much joules is per second. So 7500 of joules heat is provided in 1 second. Is it okay? As you can see the SI units, joules per second. So 7500 of joules is heat is provided in 1 second. So how much is required? 3.085 multiplied by 10 raised to the power 6 joules of heat will be provided in how much time? Will be provided in, so what will be the value? 1 upon 7500 multiplied by 3.085 into 10 raised to the power 6. So we just have to solve this, and this approximately comes out to be 411.3 seconds. Solutions you have to do by yourself, basic mathematical calculations. So this is our answer. So what we have learned from this numerical is heat needed was our target to calculate the value of time that is required, and heat released was given to us. Okay, so heat release was simply given to us. We just multiplied it by 50, and heat needed was the main aim that was to be calculated. So for this we have used the formula for delta H, that is NCP delta T. Okay, and for N we have used the ideal gas equation, which was PV is equal to nRT. N is equal to PV by RT, and volume also was calculated very easily because the dimensions are of cuboid. So that volume is equal to L into B into H. So this was a numerical. Okay, so thanks for watching, and stay tuned for more of numericals as well as theory part. Thank you.